Imagine, just for a moment, that everything you see, everything you know, well, it isn't the whole story. What if our entire universe, I mean, every star, every galaxy, every tiny particle, even time itself, what if it's just one tiny piece of something? Something infinitely, almost unimaginably larger. It's a thought that really stretches the imagination, doesn't it? Today, we're taking a deep dive into the multiverse hypothesis. Our mission really is to explore this mind-bending concept and ask this profound, almost dizzying question. Is our universe just one of many? And we've got this fascinating nugget to unpack from our source, the multiverse hypothesis, which it captures the core paradox perfectly. It says the idea is compelling but lacks direct evidence.
Right, and that's exactly the tension we want to unravel for you today. What makes an idea so conceptually grand, so intellectually, well, seductive almost? Yet at the same time, it's one we simply cannot directly observe or measure. Not right now, anyway. We'll be digging into the profound appeal of a concept like this and then, crucially, the rigorous demands of science. What does it truly mean for something to lack direct evidence in physics and cosmology? It's actually a perfect example of how these huge, potentially groundbreaking ideas are born, how they get explored and then, eventually validated. Or maybe they remain as these intriguing, unproven possibilities.
Absolutely. So, whether you're kind of new to these big cosmic concepts or maybe you follow the latest in theoretical physics, we're going to try and help you understand why this idea has captured the imagination of so many people and what its implications are for the whole process of scientific inquiry and why it offers such a powerful illustration of how we push the frontiers of knowledge forward. Let's start by digging into that fundamental question first. Okay, so our source kicks off with this really profound question. Is our universe just one of many? Now, for most of us, I think when we hear the word universe, we instinctively picture, well, everything. The sum total of all existence, right? Every atom, every star, every galaxy, space-time, the whole shebang. So what does it even mean to think beyond that? It almost feels like trying to imagine, I don't know, brand new primary color, something totally outside our existing framework.
You've really hit on a crucial point there. Our intuitive understanding of our universe is exactly as you described it. It's the totality of all that we can, at least in principle, observe, measure, and experience. It includes every star, every galaxy, every particle, every moment in time that has ever existed or will exist within, let's call it, the bounds of our cosmic reality. It's our entire known cosmic neighborhood, stretching across something like 93 billion light years of observable space. That part's key. So to conceptualize something beyond that known boundary, which is what the multiverse theory asks us to do, well, that represents a truly radical shift in perspective. It's about moving from thinking of our universe as this singular, unique backdrop for all existence to seeing it as just one instance within a potentially far grander collection. It helps to think of it through a historical lens, maybe, because humanity has had to make similar conceptual leaps before, big ones. For centuries, we thought Earth was the center of everything. Obvious, right? Then along came Copernicus and Galileo, and they showed us, no, Earth is just one planet orbiting the sun. That was a huge mental adjustment. Then, a few centuries later, we realized our solar system was just one of billions within a single galaxy, our Milky Way. Another big jump. And then people like Edwin Hubble revealed our galaxy is just one of, again, billions, maybe trillions, in the observable universe. Each of those steps required a massive expansion of our understanding, and honestly, a humbling reevaluation of our place in the cosmos. The multiverse theory. It proposes yet another leap, maybe the grandest one yet.
So it's not just about finding a bigger space, like discovering another continent here on Earth. It's more fundamental than that. It's changing what we even consider a basic unit of reality, that our entire cosmic existence, everything we call our universe, could be just one instance within a larger set.
Yeah, that's incredibly profound. It really shifts things, moving from this idea of a singular, unique existence to one of multiplicity. It challenges the very notion of cosmic uniqueness.
Exactly. And the philosophical weight of that concept is, well, it's immense. For centuries, like I said, our universe has been seen as the ultimate, the singular stage for everything. The idea of a multiverse just shatters that singularity and implies that what we perceive as everything might just be a localized manifestation, a bubble, if you like, within an unimaginably grander framework. It forces us to reconsider the very nature of reality itself and our unique or perhaps not so unique place within it. It's a conceptual journey from thinking about the universe as the absolute totality to maybe a universe as just one among, well, potentially many. And when we talk about many universes, are we talking like dozens, hundreds? Or are we getting into something truly mind-bogglingly vast, something that sort of defies our ability to even mentally picture the scale? Because many can mean very different things.
That's a really crucial clarification. When theoretical physicists discuss the multiverse, the implication is rarely just, a few more universes next door, or even thousands. Depending on the specific theoretical models that point towards it, things like eternal inflation or string theory landscapes, the implication is often an infinite number of other universes. And that's where it really starts to challenge our notions of uniqueness and cosmic significance, doesn't it? If there are an infinite number of universes, then the possibilities for what those universes contain, what laws they might follow, what forms of existence they might harbor, well, those possibilities become equally infinite. And this sheer scale, this potential infinity, that in itself is a significant part of what makes the idea so compelling, to use our source's word. Think about it. If our universe appears remarkably fine-tuned for the existence of life, with physical constants seeming just right, and if we struggle to explain why it happens to be so perfect for us, well, the multiverse offers a kind of conceptual answer. If there are infinite universes out there, trying out all possibilities, then it's maybe not that surprising that at least one of them, like ours, would happen to have the conditions necessary for life to emerge. It sort of turns what looks like a miraculous occurrence into almost a statistical inevitability. Now, this is a conceptual answer, right? Not an observation. But it's immensely appealing to many scientists grappling with these really deep questions about existence.
Yeah, that concept of statistical inevitability, that definitely resonates with the whole compelling aspect. Let's dig a bit deeper into that. Our source specifically uses that word, compelling, to describe the multiverse idea. Why do you think such a monumental concept, one we can't actually see or touch, grabs our attention so powerfully? What is it about us, about the human mind, that finds this idea so incredibly appealing?
That's an excellent question. And I think it speaks to the very core of human curiosity, doesn't it? Our fundamental drive to understand. There are probably several deep-seated reasons why the multiverse idea resonates so profoundly with us, making it feel compelling, even without that direct proof we talked about. First off, it just taps directly into our inherent curiosity and wonder. I mean, humans have always looked up at the night sky and asked, what's out there? Where did all this come from? What lies beyond the horizon? The multiverse takes that ancient impulse and pushes it to its grandest possible extreme. It's the ultimate frontier, right? It offers this conceptual landscape of possibilities far beyond anything we've ever really imagined. This deep-seated desire to understand origins, existence, what lies beyond our immediate perception, that's a really powerful driver. For science, for philosophy, for everything, we are, fundamentally pattern-seeking creatures. And the idea of some ultimate pattern that encompasses all reality is incredibly attractive. Second, it seems to provide potential frameworks, maybe even answers, for some of the most profound existential questions humanity has ever asked. Questions like, why are we here? Are we alone? Why is the universe the way it is and not some other way? The multiverse offers this grand narrative that, okay, yes, it's speculative, but it can feel intellectually satisfying. If our universe is just one of many, it kind of recontextualizes our existence, doesn't it? It suggests that our specific reality with its particular laws and conditions isn't necessarily some unique, inexplicable fluke. It might just be one outcome among a vast cosmic lottery. And that can feel like it provides a purpose, or at least a statistically plausible explanation, for our own existence and the seemingly improbable conditions that allow life like ours.
Right, so it gives us a story, a narrative that helps make sense of things that might otherwise feel totally random or almost too specially configured, like a cosmic explanation for what might seem like a miracle.
Exactly. And then there's just the sheer appeal of infinity and vastness. There's a certain intellectual allure, almost a dizzying fascination, with concepts that push the boundaries of our understanding of scale and possibility. Our minds are kind of captivated by the idea of something endless, something boundless. You see it everywhere, right? Infinite numbers in math, the concept of eternity in religion, the sheer vastness of the cosmos in astronomy. Humans have long been drawn to the infinite. The multiverse, implying potentially an infinite array of universes, well, it challenges our cognitive limits and offers this boundless playground for the imagination. It's a concept that feels truly monumental, and our minds are instinctively drawn to monumental things. For some people, thinking about it is almost a spiritual experience, a humbling reminder of how much there might be beyond our immediate grasp. And finally, maybe more practically, from a theoretical standpoint, even without getting into the nitty-gritty math, the idea of a multiverse can offer profound problem-solving potential for certain cosmological puzzles. For instance, when scientists look at aspects of our universe that seem, well, inexplicably just right or finely tuned, like why the strength of gravity or the mass of an electron or the initial expansion rate after the Big Bang have the precise values they do, values that seem necessary for stars, galaxies, and ultimately life to exist. Explaining that in a single universe framework can be really tricky. These are sometimes called anthropic coincidences. But if you introduce the concept of, say, an infinite number of universes, each maybe with different laws or different initial conditions, then the existence of our seemingly special universe becomes less of a deep mystery and more of a statistical inevitability. It's like a cosmic version of the lottery, right? If there's only one ticket sold, winning feels miraculous. But if there are infinite tickets sold, someone is guaranteed to win. And it's no surprise that we happen to be in the universe that won the cosmic lottery because we couldn't exist to observe it if it hadn't. So it can seem to complete a conceptual framework, even if that completion is, at this stage, purely speculative. It suggests an elegant, if currently untestable, solution to certain deep cosmological puzzles that otherwise leave scientists, well, scratching their heads.
Okay, so for someone like you, our listener, trying to quickly get your head around these big ideas, what makes this compelling aspect really resonate? Is it that potential for those aha moments where something just clicks into place or where a seemingly impossible problem suddenly seems to have a conceptual pathway to a solution?
Absolutely. The potential for aha moments is huge here, precisely because it offers this very elegant, almost simple way to resolve what seems like an astonishing coincidence in our own universe. The idea suggests, like we said, if there are infinite universes, then the probability of a universe like ours existing with its specific laws and conditions that allow for complexity in life becomes less extraordinary. It becomes more like an inevitable outcome within this vast cosmic ensemble. And that can be a significant conceptual breakthrough for many people, like rolling dice an infinite number of times. Eventually, every possible combination will come up. So if each role is a universe, then a universe like ours that seems to require a very specific combination of conditions for life, well, it's bound to show up somewhere, sometime. And that realization, it recontextualizes our place in the cosmos completely. We shift from thinking we're in a singular, potentially unique reality where our existence might seem miraculous or even, some might say, designed, to potentially being part of a much larger, much more diverse cosmic landscape. It shifts the core question from why this universe?
To maybe, why not this universe among infinite possibilities? But that's it. And that shift in perspective itself is often the source of the aha moment. Realizing the profound implications of such a vast conceptual framework for how we understand reality, probability, and our own existence, it kind of makes the seemingly impossible possible purely through the power of sheer scale. It's a powerful intellectual tool, even if it's currently just that, a conceptual tool.
That statistical explanation is definitely compelling, but, it almost sounds too easy. Are there criticisms of that particular answer? Does it maybe just push the problem somewhere else or simplify things too much?
That's a very perceptive question. And yes, absolutely, there are significant criticisms along those lines. While the anthropic principle, combined with the multiverse, offers this elegant potential solution to the fine-tuning problem, some physicists and philosophers argue that it's not truly explanatory. They sometimes call it a cop-out or maybe a multiverse of last resort. The core criticism is that it doesn't actually explain why the fundamental laws and constants are the way they are in any given universe. It just posits that if they can vary across universes, then ours is just one random outcome we happen to observe because we couldn't observe the others. It sort of pushes the fundamental question of origins up a level to the meta laws that might govern the creation or existence of these multiple universes. It doesn't answer, well, why do those meta laws exist? And maybe even more significantly, it makes the whole idea incredibly difficult to test scientifically, which brings us right back to the other crucial half of our paradox.
Right. So if an idea is this compelling and it offers these potentially elegant solutions, does that automatically make it true? Or does it just mean, okay, this is really interesting, it's worth exploring further?
This raises an absolutely fundamental question in science, and it highlights a critical distinction we have to make. A compelling idea, like the multiverse, serves as a really powerful motivator for scientific inquiry, no doubt about it. It pushes researchers to explore new theoretical avenues, to develop incredibly complex mathematical models, and to tirelessly seek out potential evidence, even if none currently exists. The sheer allure of the multiverse definitely sparks the imagination, which is often the very first crucial step in any scientific discovery. Think of it like a tantalizing signpost pointing towards a potential new frontier of knowledge. But that's just the start of the journey, right? The compelling nature isn't the destination itself, it's more like the fuel for the engine of scientific exploration. The next step, the absolutely indispensable step, is always the search for evidence. Which brings us neatly to the other half of our source materials statement.
Okay, so our source is very clear on this flip side of compelling the multiverse lacks direct evidence. Now, for someone maybe unfamiliar with scientific methodology, what exactly does direct evidence mean in this specific context? And why is it so absolutely crucial? Because, for some people, a compelling idea might feel like evidence in itself.
That's a vital distinction to make, and honestly, it's the bedrock of scientific proof. In science, direct evidence typically means something that can be, observed, measured, or detected through experiments or astronomical observations. Something that unequivocally supports or refutes a specific hypothesis. It's about empirical data information gathered through our senses, or more often, sophisticated instruments that points directly to the existence or properties of the phenomenon you're investigating. For example, when Galileo pointed his telescope at Venus and saw its phases, that was direct observational evidence. It directly supported the Copernican idea that Venus orbits the sun, not the Earth, because the phases he saw just couldn't be explained otherwise. Or when astronomers observe the redshift of distant galaxies, that's direct evidence that our universe is expanding. More recently, when experiments like LIGO detected gravitational waves, that was direct evidence of massive cosmic events like black holes merging, and it directly confirmed a key prediction of Einstein's theory of relativity. These are concrete, measurable phenomena that either confirm or deny a specific hypothesis. And crucially, true direct evidence also implies repeatability and verifiability. This is key. Other scientists, using similar methods or independent methods, should be able to make the same observations or achieve the same experimental results. This allows for independent verification, which is absolutely paramount in solidifying any scientific claim. It guards against errors, biases, and fraud. Now, for the multiverse, direct evidence would mean something like a tangible, empirical observation of another universe itself, or maybe its direct, undeniable effects on our universe. And that, obviously, is a very, very high bar, because by definition, these are potentially separate entities, maybe causally disconnected from us, possibly beyond the reach of our current instruments, and maybe even our current understanding of physics.
Right. So it's not enough just to have a really elegant mathematical model or a theory that beautifully explains certain cosmic puzzles conceptually. You actually have to see something or measure something tangible from this other supposed universe, or maybe a direct imprint it leaves on ours. That sounds like a massive hurdle to overcome.
Precisely. And if we connect this to the bigger picture of how science works, science isn't just about compelling ideas, right? Nor is it merely about elegant mathematical frameworks, beautiful as they might be. It's fundamentally about testable ideas. Without direct, empirical evidence, even the most elegant, the most intuitively satisfying, or the most conceptually grand concepts have to remain in the realm of hypothesis or speculation. They are possibilities, fascinating ones perhaps, but they aren't established scientific realities. Direct evidence is what grounds a theory in the physical world. It's what allows us to move beyond what we imagine could be true to what we can actually demonstrate is true based on observation and experiment. The scientific method, really at its core, demands this. It's not, popularity contests based on how cool an idea sounds or a beauty contest based on how elegant the math is. It's fundamentally about observation and experiment. If a hypothesis cannot, even in principle, be tested against reality, if there's no conceivable way to prove it right or wrong through observation, then it tends to remain more of a philosophical idea rather than a strictly scientific one.
And this is exactly why the lack of direct evidence for the multiverse is such a critical point, even given its profound allure and theoretical motivation. It keeps it firmly in the realm of an active area of research and speculation, but not yet a validated scientific theory.
So without that direct evidence, an idea, no matter how cool it sounds or how much it seems to help explain things conceptually, it just can't really become a fully accepted scientific theory. It kind of remains in this theoretical limbo, waiting for proof.
It's exactly right. Direct evidence is what promotes a hypothesis from being a what-if scenario to being part of our what-is understanding of the universe. It's the absolutely critical step in validating a scientific theory. It allows us, as a scientific community, to distinguish between these fascinating possibilities and the realities that are supported by empirical data. Without this empirical anchor, a concept, no matter how intellectually appealing or theoretically motivated it might be, just doesn't graduate to the status of a widely accepted scientific theory. It remains a powerful idea, one that definitely sparks research and fuels imagination, but it lacks that observational bedrock that defines scientific certainty or at least high confidence. And honestly, acknowledging this lack of evidence is a testament to the rigor of the scientific method itself. It's a statement of scientific integrity, acknowledging the current limits of our knowledge and observational capabilities.
Okay, so what are the practical implications then? When you have an idea as compelling, as potentially revolutionary as the multiverse, but it still has no direct evidence backing it up, how does the scientific community actually treat it? Do they just sort of set it aside and say, come back when you have proof? Or is there a way they continue to engage with it seriously?
Well, not at all. It's certainly not just set aside. The practical implications are significant, yes, but it definitely doesn't mean the idea is dismissed out of hand. First, it clearly means there are challenges for widespread acceptance. The idea is simply not accepted as a proven scientific theory within the mainstream scientific community. While many theoretical physicists are fascinated by it, work with multiverse models conceptually, and find them theoretically promising, they would almost all be very quick to acknowledge its current unproven status. It's treated as a hypothesis, a theoretical model, maybe a framework for thinking, but not yet a validated description of reality. So this means it doesn't typically appear in fundamental physics textbooks as established fact, right? It's presented, if at all, as an area of active, cutting-edge, and often speculative research. It's debated, it's explored theoretically, but it's not yet part of the scientific canon. Second, it means it remains a very active area of theoretical physics and also philosophy, but crucially, without those empirical anchors we talked about. Researchers continue to explore the theoretical implications, develop more sophisticated mathematical models that might predict its existence under certain conditions, and even ponder how, if it were real, we might eventually detect it. Even if those detection methods are currently far beyond our technological capabilities, or perhaps even theoretically impossible, it exists in that fertile ground of unproven but highly interesting, highly motivating speculation. And frankly, this is where a lot of cutting-edge, often really mind-bending research takes place right at the very edges of what we currently know and can test. Third, and this is perhaps the most challenging aspect scientifically, is the inherent difficulty in falsification or verification. Without direct evidence, it's incredibly hard, maybe impossible, to design experiments or observations that could either definitively prove its existence or, just as importantly, disprove it. A core tenet of the scientific method, going back to Karl Popper, is that a hypothesis must be falsifiable. There must be some imaginable observation or experiment that could show it to be false, if it indeed is false. For the multiverse, its very nature, potentially separate universes existing outside our observable horizon, our light cone, or maybe in other dimensions, or perhaps operating with completely different physical laws, makes direct testing extremely difficult. Our light cone defines the region of the universe we can ever observe or interact with, because information can only travel at the speed of light. If another universe is causally disconnected from ours, or just too far away in some higher dimensional metaspace, then we simply can't see it or its effects directly. This is a huge hurdle for any scientific concept aiming for validation. And finally, the very statement that it lacks direct evidence actually reflects the rigor of the scientific method in action. It's not meant as a dismissal or a criticism of the idea itself. It's an honest, objective assessment of its current scientific status based on available data. It serves as a clear call for empirical proof, demanding more than just conceptual elegance or theoretical motivation. It reminds us that no matter how much an idea makes intuitive sense to us, or how compelling it feels, science ultimately requires observation and data to transition from being a fascinating possibility to becoming an established reality. It holds even the grandest, most exciting ideas to the highest standard of empirical verification.
Okay, so how does science, and maybe the scientific community more broadly, actually operate when faced with this kind of situation? A super compelling idea that still eludes any direct proof. It must be a tricky balance to strike, right? You want to explore these exciting possibilities, but you also need to remain grounded in evidence. It sounds like a constant tension.
It is indeed a tricky balance, yeah. And it perfectly illustrates that science is this dynamic, iterative process. It's not just a static collection of facts written down in books. Ideas like the multiverse often start as conceptual frameworks or mathematical possibilities that arise, sometimes quite naturally, from our existing, well-tested theories, or even from trying to explain certain puzzling observations. For instance, some interpretations of quantum mechanics, like the famous many-worlds interpretation, MWI, which was proposed by Hugh Everett. That interpretation suggests that every time a quantum measurement happens, the universe effectively splits or branches into multiple parallel universes. Each branch represents a different possible outcome of the measurement. So in one universe branch, the electron spin is measured as up, and in another simultaneous branch it's measured as down. This is one theoretical pathway that leads directly to the idea of multiple coexisting realities, emerging from the mathematics of quantum theory itself. Another really prominent example comes from inflationary cosmology. This is the idea that our universe underwent an extremely rapid exponential expansion phase, just fractions of a second after the Big Bang. It explains a lot about the universe we observe today, like its flatness and uniformity. Now, some models of inflation, particularly those known as eternal inflation, suggest that this rapid expansion process might not have been just a one-off event that happened in our patch of space-time. Instead, the underlying mechanism could be ongoing, continuously spawning or budding off new bubble universes elsewhere in a larger metaspace. Each bubble universe would undergo its own Big Bang, inflate, cool down, and potentially have different physical constants and laws determined by chance during its formation. In this picture, our entire observable universe would simply be one such bubble within an infinitely expanding, possibly fractal-like multiverse. Then you also have ideas emerging from string theory, specifically the string theory landscape. String theory attempts to be a theory of everything, unifying quantum mechanics and general relativity. It posits that fundamental particles are tiny vibrating strings. The theory seems to allow for an absolutely enormous number of possible ways. The extra dimensions it requires can be curled up, maybe 10 to the power of 500 or even more. Each configuration could correspond to a different universe with different properties and fundamental constants. Our universe, then, is just one specific vacuum state or solution within this vast landscape of mathematical possibilities allowed by the theory.
Wow, okay, so these aren't just like completely random ideas pulled out of thin air. They actually stem from trying to extend or interpret our best, albeit still incomplete, theories about how our own universe works, quantum mechanics, cosmology, string theory. So even without direct observation of other universes, these ideas are explored seriously because they seem to emerge naturally from the physics we do understand, or are trying to build.
Precisely. That's a key point. Even without that direct smoking gun evidence, these ideas are pursued vigorously because they can offer elegant potential solutions to existing puzzles, like fine-tuning or the nature of quantum measurement. And because they seem to arise naturally from deeper theoretical frameworks that scientists are already working on. So researchers continue to develop these theoretical models. They explore potential indirect implications that might be testable someday, and they actively search for any potential avenues for detection, however slim the chances might seem now. This might involve looking for subtle, unusual patterns or anomalies in the cosmic microwave background radiation, the faint afterglow of our own Big Bang. Some theories suggest a collision with another bubble universe in the distant past could leave a detectable bruise on the CMB. Or it might involve searching for theoretical consistency, looking for ways these ideas could lead to a unique, testable prediction within our own universe, even if it's not direct observation of another one. It really is a testament to the persistent, almost relentless pursuit of knowledge that drives science. Even when the answers are incredibly challenging, to obtain and lie right at the very edge of our current understanding and capabilities. And yeah, as a physicist working in related areas, I can tell you the sheer conceptual scale of the multiverse is sometimes hard for even us to truly wrap our heads around. But that difficulty doesn't make it any less fascinating or less important to explore theoretically. Scientific progress often involves these cycles, doesn't it? We start with these compelling ideas, maybe born from theory or unexplained data that spark our imagination. Then we develop new theoretical tools, new mathematical methods to explore these ideas more deeply and rigorously. Next comes the often long and painstaking search for evidence. This frequently requires building entirely new kinds of technologies, new telescopes, new particle accelerators, or designing incredibly novel experiments that push the boundaries of what's technically possible. And then, based on the evidence that eventually emerges or fails to emerge, the original idea is either confirmed or perhaps modified, or if no evidence is found and it remains fundamentally untestable, it might be eventually put aside, or it might remain in that realm of fascinating but ultimately unproven hypotheses. The multiverse, right at this moment in scientific history, is very much in that intense search for evidence phase, coupled with a lot of ongoing theoretical development trying to refine the ideas and look for testable consequences. It's a genuinely open question, and science absolutely thrives on confronting these big open questions.
Okay, so let's bring this back to our listener. What is this whole deep dive into the multiverse, focusing on its compelling nature, but also its very real lack of proof? What does this mean for you listening right now? Why should you care about the specific paradox, this tension between something so incredibly alluring and something so lacking in concrete, verifiable proof?
That's a great question to end on. I think this deep dive offers a really powerful insight into the very nature of scientific discovery itself.
something far broader than just a specific concept of the multiverse. It shows us vividly that science isn't just a collection of neatly packaged facts that have all been checked off and confirmed. Not at all. Instead, it's this vibrant, messy, ongoing process of asking truly colossal questions, exploring incredible, sometimes almost unbelievable possibilities, and then, critically, rigorously, seeking evidence to either support or refute those possibilities. It reminds us that, especially at the frontiers of human knowledge, there are often far more questions than definitive answers. And that's okay. That's actually what drives progress. It also teaches us, or perhaps reminds us, to appreciate the crucial distinction between a fascinating idea, a beautiful mathematical model, or a really compelling narrative, and scientifically validated truth. When you encounter new information, especially in complex scientific fields, understanding this distinction is absolutely essential for good critical thinking. It encourages you, hopefully, to ask, okay, is this just an interesting idea, a cool speculation, or is there solid empirical evidence to actually back it up? And this ability to differentiate between speculation, however exciting, and established scientific fact is incredibly valuable in navigating our modern information-rich world. Whether you're learning about cosmology or climate change or medicine, or even just evaluating a news story you saw online. Furthermore, it highlights that even at the very frontiers of human knowledge, in fields like advanced physics and cosmology that seem so sophisticated, fundamental questions remain wide open. The journey of discovery is definitely far from over. It's a dynamic, constantly evolving landscape where groundbreaking concepts are always being born, debated fiercely, and rigorously tested against observation. Understanding the multiverse hypothesis and its current somewhat ambiguous status gives you a fascinating window into how science truly operates at its cutting edge, grappling with the profound unknown and constantly pushing the boundaries of what is knowable. It demonstrates quite beautifully, I think, that the greatest mysteries often come hand in hand with the greatest intellectual allure. And it's this combination that drives scientists forward, even when the path ahead is deeply uncertain and the answers are incredibly hard to find.
So we've journeyed into this profound, maybe even unsettling idea of the multiverse, a concept that is, as we've discussed, undeniably compelling. It inspires wonder, it stretches our understanding of reality, it suggests our entire universe is just one tiny part of something vastly larger, perhaps infinitely larger. Yet, as our source material clearly states, and as we've explored, it currently lacks direct evidence.
And this tension, this inherent conflict between compelling imagination and the absolute necessity of empirical proof, really lies at the heart of so much of scientific inquiry. It reminds us that while brilliant ideas can certainly spark discovery and guide our theoretical explorations, it's ultimately the evidence, the data, the observations that solidify our understanding of the universe. Evidence is what moves concepts from the realm of exciting possibility into the realm of established reality. It is the very engine of scientific progress, constantly demanding that we verify even our grandest and most appealing ideas against the often unforgiving backdrop of physical reality.
So what does this all mean for you, thinking about this now? As you consider the possibility of other universes, maybe just pause and think about this. What makes you believe something is true? Is it how compelling an idea feels, how much it resonates with your intuition, or how well it seems to help you make sense of things? Or is it the rigorous, verifiable evidence you have to support it, the hard-won observations and data that truly anchor an idea in reality?
And looking forward, as our scientific instruments inevitably become ever more powerful, or perhaps as new theoretical breakthroughs emerge that we can't even conceive of today, how might the continued scientific pursuit of direct evidence for something as truly grand as the multiverse, or maybe its continued frustrating absence, how might that shape our future understanding, not just of other potential universes, but perhaps of the very nature of truth itself, especially in a world that seems increasingly filled with compelling narratives that may or may not be grounded in verifiable fact?
Something profound to ponder indeed. Until our next deep dive, thank you so much for joining us.